Traveling for hundreds of thousands of miles per day, yet always in sight of home. The product of a bold past, but also the bridge to an ambitious future. Designed to make spaceflight routine, it has taught us our most painful lessons about the danger that lurks whenever humans journey beyond our home planet. This is the legacy of the Space Shuttle, a vehicle that for over 3 decades came to define human spaceflight, while helping to create a permanent presence in orbit. But for scientists, the fleet of space shuttles also meant something more. They were traveling laboratories with access to the unique environment and perspective of low Earth orbit. Impossible to reproduce on the ground, this was to be the setting where astronaut researchers would test the limits of materials, the universe, and even their own bodies. All essential information that could one day help humans venture much farther into deep space. Of the 5 shuttles that blasted off from Cape Canaveral, only 3 remained. But despite the tragic loss of Challenger and Columbia, the program successfully completed 133 missions. And nearly 150 astronauts have flown in a shuttle, many of them making several trips.
The space shuttle may have completed its final journey, but over 30 years, it's managed to transform spaceflight by making it just a bit more routine, even as it's taught us that extreme exploration still comes with tremendous risks. The shuttle has also blazed a trail for science in space, a trail that continues aboard the International Space Station.
Today, the idea of a continuous presence in space in support of scientific research is no longer a dream. But it took the shuttle program to get there, and that took an act of true vision. In 1969, the same year that Neil Armstrong first walked on the moon, a small group of engineers in the California desert had a job to do. It was to build a vehicle to ferry people back and forth to low Earth orbit. Known as STS, for Space Transportation System, this new kind of spaceship wasn't going nearly as far. And to be affordable, it would have to be reusable, a space plane that could survive both liftoff and re-entry. These early test models were dubbed flying bathtubs because of their clunky shapes. But what they lacked in grace, they made up for in stamina. Designed to deflect heat away from the crew cabin, the vehicle's wide underbelly was the key that would allow it to endure the searing, high-speed descent through the atmosphere over and over again. The final shuttle design included wings for stability, a feature that would allow the craft not just to descend, but to glide into a low The design was flight tested by releasing the shuttle from the back of a specially outfitted Boeing 747. But no flight test on Earth could reproduce the harsh environment of space. So, on April 12, 1981, the first of the shuttles to be readied for orbit sat poised on the launch pad.
6, 5, 4, we've gone for main engine start.
And as Columbia soared successfully into the sky, a 30-year journey for science on the shuttle was set to begin. With better access to space than ever before, researchers had a long list of topics they were eager to explore with NASA's new orbiter. And the first subject of serious study from the space shuttle was the one that was visible just outside the crew cabin windows: Earth. By now, views of our planet from a few hundred kilometers up were a familiar sight thanks to earlier chapters of the space program. But with bigger windows than the space capsules of the 60s and 70s, and with better technology to take advantage of that view, the shuttle raised Earth observation to a new level. This effort was already underway by the second space shuttle mission, which carried an imaging radar, a way of bouncing microwaves off of Earth's landforms to build up a detailed picture of our planet's diverse geography. The radar system proved to be a powerful tool for Earth scientists because, unlike photography from space, it worked regardless of whether it was imaging the day or the night side of the planet. It was also unaffected by cloud cover. Flying aboard the shuttle 3 times over the next 13 years, the radar system returned alluring and spectacularly colorful views of the surface. For scientists eager to study our world from above, there was no doubt the space shuttle had arrived, and it was showing them Earth like they'd never seen it before. It's said that beauty is only skin deep. But when it comes to imaging Earth from orbit, being able to see beneath the skin is a big advantage. That was the principle behind the space shuttle's imaging radar, which not only bounced microwaves off the planet's surface, but watched them penetrate a little way into the surface, allowing the system to see hidden information in the underlying rock and soil. Here, for example, a spectacular view of Mount Etna on the island of Sicily, one of the world's most active volcanoes. It reveals the complex succession of lava flows that have spilled down the mountain's sides over many generations. Scientists compare images like these with what they observe on the ground and can use them to help explore more remote volcanoes from orbit. In another case, the dry, blowing sands of the Sahara Desert nearly conceal this curious geologic feature lying just below the surface. But because radar can penetrate the top layers of sand, this shuttle radar image of the Arunga crater in northern Chad shows what happened when a small asteroid collided with Earth hundreds of millions of years ago. The shuttle was used to study the possibility that the asteroid broke up into pieces before it struck, leaving not one crater, but a chain of at least 3 craters. Elsewhere, the same technology has also helped document more immediate changes. Here we see a shuttle radar view of Chile's vast and remote Patagonia ice fields, taken in October of 1994. In this view, red and purple indicate areas of high elevation. By comparing this image to one taken in the same shuttle mission, researchers were able to measure the speed at which different parts of the glacier are moving. Such measurements are crucial for understanding how Earth's icy regions are responding to global climate change.
We've gone for main engine start.
By the year 2000, the use of the space shuttle as a radar platform had evolved into the Shuttle Radar Topography mission, which produced high-resolution elevation data for 80% of Earth's surface. The result was, at that time, the most detailed map of our world ever made. The space shuttle also explored our home planet in other ways. On 3 missions between 1992 and 1994, it carried the Atlas experiment, designed to measure the chemistry of Earth's atmosphere and its interactions with the sun. Among its many contributions were data that support the realization that chlorofluorocarbons, or CFCs, are damaging Earth's protective ozone layer, and that their production had to be curtailed. But this was just the beginning. Throughout the 1980s and 90s, the space shuttle offered a gateway for science in space of all kinds, especially science that could take advantage of the most obvious feature of space travel: the fact that in orbit, the concept of up and down seems to vanish.
The reason things behave so differently in low Earth orbit is also what makes it difficult for humans to work there: microgravity. As the shuttle orbits, it's actually falling around the Earth. Everything in it is falling too. Earth's gravity is still there, but its effects are no longer felt. This microgravity environment affects every aspect of spaceflight, from the design of the toilets to the way we might expect to grow plants for food in the future.
Without gravity as a guide, plants have no sense of down. Roots sometimes grow in the same direction as leaves. The effects of microgravity extend even to the smallest scales. In one startling shuttle experiment, salmonella bacteria were shown to become more active in space. Working with the space bacteria, scientists were able to identify the gene that switches on this behavior, a possible step toward developing a protective vaccine against salmonella, one of the most common causes of food poisoning. But humans are also not immune to the effects of spaceflight. In perpetual freefall, the gravitational cues that the body relies on for everything from muscle development to circulation to perception are gone. And while the sensation of flying in space can be liberating, at the physiological level, microgravity presents a severe challenge to the human body. One of many that must be surmounted before humans can live permanently in space. The space shuttle has been crucial to building up our understanding of what happens to the body when it's in space. But perhaps most important of all, starting in the late 1990s, the space shuttle became the essential tool for creating the International Space Station. a more ambitious and longer-lasting presence in space, and a stepping stone into the future. And with human spaceflight reaching for new heights, so too were the scientists eager to make use of the new facility to extend human knowledge into new frontiers. From the moment the first space shuttle took flight, humanity was on a new path. One that made low Earth orbit a familiar destination for an entire generation of astronauts. But the shuttle was, first and foremost, a vehicle, not a port. Even the longest shuttle missions were rarely over 2 weeks. To realize the full scientific potential of low Earth orbit for many types of experiments, researchers needed a permanent laboratory rather than an occasional visit. So, to establish a new outpost in space for a new century, NASA, the US Space Agency, teamed up with Russia, Europe, Japan, and Canada to create the International Space Station, one of the boldest construction projects in history. Of course, the shuttle would play a key role in building the station. Starting in 1998, it began ferrying up many of the modules and other elements needed for the giant habitat. In combination with the pieces lofted up by Russian Proton and Soyuz rockets, the massive station gradually began to take shape, reaching its completion only with the final few shuttle flights some 13 years later. During those years, the space shuttle became less available to scientists eager to pursue experiments in orbit. But the end result is something far grander and more versatile. By November of 2000, long before the station was completed, astronauts began arriving for the first long-duration missions to the station. The station has been occupied ever since, setting a new record for continuous human presence in space. In its current form, the space station accommodates 6 astronauts, giving researchers an unprecedented platform from which to conduct experiments in life sciences, materials science, earth science, and astronomy. And with a construction cost nearing $100 billion, NASA and the other partners behind the station are eager to get the most benefit possible out of the facility. In May of 2011, during what would be the second-last space shuttle mission, astronauts delivered a final piece of scientific apparatus to the station. An unusual detector designed to probe some of the most powerful and mysterious energy sources in the universe. It's called the Alpha Magnetic Spectrometer 2, a device that counts and measures the high-speed particles coming from all directions in space, known as cosmic rays. Thought the most powerful cosmic rays are generated by supernova explosions and giant black holes. But some may point to even more exotic processes at work in the cosmos. The trick is seeing enough of them to spot the types of cosmic rays that are truly rare. The vast majority of these particles are ordinary cosmic rays that are already well understood by scientists. But it's also possible that a very few of them will carry hints of an exciting discovery, possibly revealing whether other parts of the universe are made of antimatter, or else helping to identify the nature of the dark matter that astronomers suspect is everywhere around us, but completely invisible to ordinary telescopes. In more practical terms, the AMS-2 will give scientists their best information yet about the high-energy particle environment in our solar system. This knowledge is crucial for understanding how astronauts may one day avoid the hard radiation exposure that is one of the main hazards of a long interplanetary voyage.
Having fired the imagination of a generation, its place in history secured, the space shuttle pulls into port for the last time.
Following the final flight of the space shuttle in July of 2011, a new chapter was opened for the International Space Station. One in which private spacecraft, like the Dragon capsule built by SpaceX, take up some of the work of bringing supplies to the station.
With private companies servicing the space station, the hope is that NASA can move on to more challenging destinations, like taking humans back to the moon, or the asteroids, or Mars. Meanwhile, the International Space Station will continue to provide a platform for science in space. Some wonder if the station has been worth all of the trouble and expense to build, but its true legacy may be in setting the stage for a longer-term human presence in the solar system.
Oh, this is fantastic. Looks nice.